Hello, this is Patrick O'Shaughnessy, and this is the 17th module in the series Statistical Methods for Analyzing Data Obtained in the Lab or Field. And here we'll discuss the two-way ANOVA analysis when you have two factors at various levels of each. So you can see from the module map that we are now at the end of the series associated with multi-sample testing. And this is as far as we'll go. There are additional types of analyses that can go beyond this two-way concept, but this is as far as this series will take you under the assumption that much of what is performed in a lab or field-based setting is rarely going to involve more than two factors at any given time. And so we'll start here. As you can see, you should have already reviewed modules 13, 14, and 15 prior to seeing this one. So here we're discussing a two-factor factorial experiment, and recall that a factorial experiment is one in which you ensure that all possible combination of the levels of the one factor or multiple factors are incorporated into the experiment in order to determine the outcomes for each of those what we call treatment combinations, right? So for example, we have two factors, and this is what was discussed in the previous module. We had cutting speed and mortar type, and there was three levels, for example, for this factor A and two levels for a factor B. And of course, we just do simple multiplication of 3 times 2 to understand that there will be 6 different treatment combinations that we'll have to keep track of and ensure that we have observations from each one of these treatments. And again, in review, if it's a balanced design, then there is an equal number of observations in all 6 treatments. So if we choose an N of 3, then 6 times 3 equals 18 total samples that were taken for this experiment. Now, when we jump from one factor to two factor, we are then able to incorporate kind of a simultaneous analysis of the null hypothesis associated with factor A, which is all the means of the 3 levels are the same, right? Mu1 equals mu2 equals mu3, and simultaneously whether or not mu1 equals mu2 for factor B. So that's what we call the significance of the main effects. Factor A and factor B are the main effects. We talked about that in module 14. We also brought up this concept of interaction. So that is also a possibility of determining whether or not interaction occurs between the factors while we're trying to make these observations. And again, in that module 14, we came up with this mathematical equation here to try to kind of enumerate it in this sense of a kind of a multivariable regression analysis where we have the slopes, beta 1 on x1, which is for factor A, and in this regression analysis, we think of x's, so x2 is factor B, and then the multiplication of the two, as you see here, is the interaction. So it is this ability to analyze the interaction that is kind of one of the benefits of applying a strict two-way ANOVA analysis to a two-factor experiment. Without incorporating this specific design type, you can't get at the interaction, as we discussed in the previous module, where you're kind of cherry picking the treatment combinations, and you don't get all possible. You don't have a full factorial design. So, for example, here, typically two factors that affect a measurable outcome are, say, evaluated under the assumption that there is no relationship between the two factors, x1 and x2. There is nothing about the way that you measure the outcome variable when x2 is fixed and you change x1, right? You change x1, you expect an outcome difference just due to changing x1 while x2 is fixed. And the same thing with x2, and we fix x1. So there's only an effect of x1 on y, or an effect of x2 on y, while the other is fixed. This is the case of no interaction. This is what we hope for, that the two factors we have chosen do not interact with each other, literally, in the way that any one of them causes the response variable to change, if that makes sense. The effect on y due to a change in one variable is independent of the value of the second variable. It is a definition of no interaction. So that would be the case here where we have our model again. It's in this case a two-variable, multivariable regression model. So you can see the first beta naught plus beta 1 x1 is a typical simple linear regression. We're now just adding on beta 2 x2 and this epsilon to take care of all the randomness in our measurements. That is what we hope for. That is what we expect. So again, we set x1, fix it, and we can vary x2. We're going to then be able to determine this slope factor beta 2, and we hope that it's significant, which means when we change x2 from one level to another level to another level, there is a difference in y. Okay, so this is kind of the relationship also between ANOVA analysis and regression analysis, which is they're completely, in a sense, mathematically related. Okay, so what happens when we have interaction? Again, occurs when the effect on y due to a change in one variable is dependent on the level of another variable. Mathematically, that involves the inclusion of an additional term here where, in this case, this beta 3 slope is significant, that it is not equal to 0. So that's kind of the null hypothesis here of all those betas. Is it equal to 0, which means that particular factor has no effect on y, or in the case of beta 3, that the combined effect, you can see here, of both factors has no effect on y, in which case beta 3 is very close to 0, and as we can state by some statistical testing that no, it is definitely statistically not different from 0. Okay, and just to emphasize this one more time, a picture is worth 1,000 words. So here's the case of no interaction. And it occurs when, for example, that no matter what you set x2 at, in this case factor b, whatever level it is at, it does not influence how x1, factor a, influences y. So, for example, we have, for example, just two levels of x1, a low and a high. And when we set x2 to 1, we see that when x1 is low, y ends up at this value here. And then when x1 is high, we have this increase in y. So there's a positive association between x1 and y. Beta, the slope, is positive. Now we go ahead and change x2 to a new level, we'll call it 2. Now, for whatever reason is going on with our system, this causes y to have increased for the same level of x1 when it's low. And likewise, it's high when x1 is high, but the unit change in y relative to the unit change in x1 has remained the same, hasn't it? The slope, this, as we can see here by this parallel line, is exactly the same. Beta 1 is beta 1 is beta 1 for how x1 manipulates y, regardless of the level of beta 2. This is no interaction. Now for interaction, as you would expect now, something happens in which the level of x2 influences the way x1 influences y, if that makes sense. So for example here, again we have the same, pretend it's the same slope when x2 equals 1. It doesn't quite look like it in this graphic, but close enough. It's a positive increase. And then we change to x2, and now we see that how x1 influences y when it goes from low to high has changed. There's something about x2 now that is making the influence of x1 on y even more dramatic. It's increasing y even higher now simply because x2 is higher. So this is where interaction occurs. There is something going on there that is causing the increase in y associated with x1 to change with a level in x2. An example might be, and this is off the top of my head, temperature increases relative humidity. Now those two things are actually connected physically, right? So the relative humidity is going to change as temperature changes. So if we're looking at an outcome of the volume of a gas containing water humidity, we might expect that as we change relative humidities, that the influence of temperature on that volume is going to change in this kind of fashion, that there's going to be some sort of kind of additive effect as relative humidity is increasing, as an example of interaction. And then from the standpoint of mathematics, we have to include this if it's truly significant, and so beta 3 becomes a significant slope here. It is something significant, means significantly different from 0. That's the test on slopes most of the time. And you can see here the slope is associated with the combined influence of x1 and x2. So all of this is because we've gone from one factor for which there's no possibility of interaction, because we don't have 2, and now we suddenly have a 2-factor experiment. Now we have to include this issue of interaction and be aware of it and test for it. Okay, so this brings up a dilemma though. If your x values are fighting with each other, so to speak, then how can you say that x1 has a significant effect on y, on the outcome? You really can't, because you don't know how much, or you do realize that x2 is also influencing the way x1 is influencing y. Okay, so here are some guidelines on that. And again, it's all amazing, massive increase in complexity, so to speak, but just by adding another factor to our experiment. So we go ahead and perform the 2-factor ANOVA, and we have an interaction term in there so we can determine whether it is significant or not. If the interaction is significant, you're kind of done. The best you can do then is you can kind of do this multiple comparison for each treatment. So in the previous example, there were 3 times 2 or 6 treatments. So when A is high and B is low, that's one treatment combination. I can look at its mean, and then when A is at its second level and B is at its second level, I can look at that one. And we can do these comparisons at those combinations only, but you see they're combinations. They are not, I cannot say anything specifically about factor A's levels by themselves and what's going on between the levels of factor B by themselves. Cannot be done. Okay, so what we're hoping for again is that there is no interaction. Then we can determine the significance of the factor A and factor B. We can look to see whether or not the p-values on those factors are significant or not. And then if they're not, well, there are no factor effects. Okay, you're done. You've proven basically you cannot reject the null. And then if there are significant factor effects, well, then we can go ahead and apply multiple comparisons to the factor means. Here we had treatment means, which bundle the 2 different factors together. Here we can separate them out, looking at the multiple comparisons of the levels of factor A, and then I can do it again for the levels of factor B. So this is where you hope your experiment goes, in this direction, that there's no interaction and that there are some factor effects, and then you can tease them out to see, which one truly is different from another. This comes from the Mendenhall textbook that I referenced in the first slide. Okay, so to repeat, you have tests for the main effects are only relevant when no interaction exists between the factors, and with interaction, you can only focus on a comparison between treatment means by determining, for example, which is highest. Okay, now let's look at the ANOVA table itself. So as you can imagine, things are getting more complicated because we have two factors, not just one, to deal with. And so they have to be incorporated into the table. And as you can see here, there are the two sums of squares associated, one with factor A and factor B. And then the interaction sums of squares will also be included, as well as the error sums of squares. That's always there to end up being the total sums of squares between all four of them. So the table then includes an extra row on top of that of ANOVA, one-way ANOVA with blocking, because we need to have one for factor A with its A minus 1 degrees of freedom. So there are A levels of factor A, just to make that seem a little more obvious. There are B levels of factor B. And you can see the interaction degrees of freedom is A minus 1 times B minus 1, which kind of makes sense. And then the error degrees of freedom is this formula here, where R is the number of repetitions for each treatment. So if you want to repeat each treatment, say 3 times, then R is 3. And as you can see here, it has to be greater than 1. If R is 1, then you have R minus 1 in this equation, and it goes to 0. So you necessarily have to have at least 2 repetitions of each treatment condition in a two-factor experiment. Otherwise, in a sense, mathematically, you are reverting back to a one-way with blocking, right, which only has 1. So that's, again, kind of the difference between those two. And one-way with blocking says, well, it's a nuisance factor, so you could call it a second factor. But you can't get at the interaction term, again, because we need these extra values to get at the error here for the degrees of freedom term in order to incorporate interaction as well. So repetition is necessary with a two-factor experiment. Okay, and we'll finish with an example here of the two-factor ANOVA utilizing Excel. In this case, there's an experiment in which they're testing battery life. So many hours is the outcome in relation to different material types and different storage temperatures. And so they have two factors then. One is material type, and they have 3 different material types, A, B, and C. And they had decided to have 3 different temperatures, 15, 70, and 125 degrees. So you can see then that they repeated each treatment combination 4 times. And so there are 4 values for this treatment combination of material A at 15 degrees Fahrenheit, etc. for the others. Okay, so it has to be packaged this way in Excel, and then this part of the spreadsheet has to be highlighted before utilizing then, or when utilizing the two-way ANOVA function. And when you do that, it looks like this. So first of all, you can see that you are going to choose the ANOVA two-factor with replication process. And again, now you know why they mean with replication as versus without. And again, it's going to now give you a summary of, like they did for the one-way ANOVA, except for each of the material types here, A, B, and C, and then across the top with the different temperatures. So you get nice number of values, the sum, the average, etc., and the total averages. Now here's the ANOVA table that we're interested in. And again, we need to now know what is what when they're dealing with this. Now sample will be the material type going across this way. They call that the sample. And the columns are, as we'd expect, the temperature differences. Degrees of freedom are 2 for both because they're both an N of 3 different levels. And again, it's going to do exactly like before, compute the MS for each group, and then compute the F values, and then ultimately a P value, and the F critical. So a little hard to see, but the first thing you need to look at is the interaction significant or not? Remember, that's what that chart tells you. You need to know which way am I going in that chart. And here it shows a p-value of 0.019. That is less than 0.05. The interaction is significant. So you are stuck. This is it. We're done. In terms of, you can, even though there are p-values for the two factors that we're interested in right above them, and they are both significant as well, you cannot state anything about them because they are influencing each other. And therefore, we don't really actually know how well they individually are influencing the outcome variable. So that is the result of this particular example. So again, what we would hope for is this is greater than 0.05 for the interaction. Then we kind of cross that list. Now we're going off to the right side of that chart. Interaction is not significant. Now I can look at the p-values on the factors and determine which one of those two is significant or not, if not both of them. And by significant, it means the levels, the means of the levels within the material, so factor A, this is the sample, are they significantly different? Kind of looking at it this way. And if factor B, or in this case the columns, is significant, then you are basically comparing down this way.